Hello everyone, it's me again. For those who don't know me, my name is André Tétreault. I'm Director of Tests Diagnostics here at VibroSystM. As usual, I'm joined by my colleague, Mr. Paul Amelinckx, one of our analysts at the Tests and Diagnostics division. Mr. Amelinckx will be handling the logistics today and also will be handling all the questions, whether in Spanish or Portuguese for our Latin American and Brazilian friends. So, buenas tardes, Paul. Boa tarde, Paul.
Thank you very much, André. Boa tarde, buenas tardes. Hello, everyone. For our friends in Latin America and also Brazil, please feel free to submit your questions in Spanish or Portuguese. We will be glad to answer them as well. Para nuestros amigos en América Latina, incluyendo Brasil, ustedes también pueden formular sus preguntas en español o en portugués, las que responderemos con mucho gusto.
So, good afternoon. As you can see, we made a slight hour change to try to accommodate some of our Pacific Coast friends. Welcome to our fifth Q&A session live on YouTube, directly from our head offices here in beautiful Montreal, Quebec, Canada, where it's a little colder today, or the past few days, so I guess fall is just around the corner. I'm very happy to be here today, as in the last Q&A sessions, and today we're going to be discussing, among other things, end winding basket monitoring issues. We have two case studies to look at today, one on the turbo side and one on the hydro side, if we have time.
Remember that to be able to submit your questions during the Q&A session, you need to log on with your YouTube account.
Correct. So you can watch the YouTube live session without connecting, but if you do want to ask questions, you do need to connect to your log on to your YouTube account. As mentioned in our previous Q&A sessions, our objective is always to answer as many questions as possible. And as was the case in the last Q&A session, there were some questions that we just didn't have time to answer, and some of the questions were asked after the session was over. So we'll begin with remaining questions, and then as new questions come along, we'll answer those. And at some point, we'll introduce the end winding vibration monitoring case study we have from a combined cycle power plant in the US. And again, as I mentioned, if we have time, we'll look at a case study for end winding vibration on a hydro generator in Quebec, Canada. So we, as I mentioned before, we're going to go through questions that we received during the session or we received after the session. So Paul?
Yes, our first question is from Poland. This question is, what is the criteria to install accelerometers to monitor end winding vibration in turbogenerators? Do international standards exist in this regard?
Well, the answer to the second question is no. There are no international standards, and I'll get back to that in detail. The criteria to install accelerometers, fiber optic accelerometers on end windings, in fact, there's four. There's four that I use, and I talk about those in our training courses, and I've talked about it in the few papers I've published. The first one, evidently, is if you've had a major failure. You know, if you had a phase-to-phase or a phase-to-ground major fault on the unit, and you get the repairs done, and you want to put the unit back on service, but it might be a good idea to make sure that doesn't happen again. So the purchase, installation, and commissioning of a end winding monitoring system can be very crucial for you to first and foremost prevent it happening again, but also may give you some clues as to exactly what happened. In some cases, the damage is so significant that other than just seeing the damage, you're not exactly sure what happened, and that's happened in many cases. So if you want to make sure it doesn't happen again, definitely sensors will be installed primarily where the failure occurred, and then possibly all around the basket to get a reference or an idea of how the entire basket is performing. The second one, I guess the most popular one, is when you go through a planned outage and you open the end bells and find clear evidence of vibration, evidence such as localized dusting or greasing. If the unit has some humidity, that dusting will turn into grease. That's a clear indication that you have some localized vibration. So you want to take care of that, try to stiffen everything up, and then install some sensors to make sure you did a good job of fixing the issue. But in some cases, the dusting is all over the place. Either vibration is rampant everywhere, or the vibration is causing some dusting, and that dust is being transported or spread everywhere around the unit because of the ventilation system. In those cases, after cleaning everything up, I would suggest doing bump tests to make sure you can identify potential bars that are vibrating during operation, and install sensors at those locations to see how they behave when the unit's in operation. Third, which is not very common, but it is in fact, the case study we have today is one example, is a new power station that's installing a new unit, or an existing power station that installs a new generator. And before commissioning, you learn that a similar unit or an identical unit somewhere else experienced significant issues. In fact, in this case, there was a major failure within a year for the same type of generator, and this utility wanted to make sure it didn't happen to them. So in those cases, you have some information as to what occurred elsewhere, and you use that information to try to protect yourselves by installing equipment and measuring the vibration to make sure that your unit is in good shape. And the fourth one is there is no evidence of vibration. You have no information that you have issues, no failures, no evidence of greasing or dusting once you go through an outage, and you just want to be proactive and protect your asset. In some cases, to get better insurance prices. Some insurance companies will give you a better price if you have, or if you can prove that you are being proactive in protecting your asset. In those cases, most of the time, the sensors are installed symmetrically all around the consolidated basket. I strongly recommend using bump tests. Bump tests might indicate some specific problems that you can address before installing the equipment, and then before putting the unit back in service. So there's four primary concerns. After a major failure, after finding clear evidence of vibration during an outage, information coming from another power plant that a similar or identical generator had issues, serious issues, and you want to prevent that, or you simply want to be proactive and protect your asset. Now, in regards to standards, unfortunately, there are no international standards on end winding vibration. You may find some documentation. For example, there's an EPRI guide that is available. It's very expensive. Unless you are a member of EPRI, then it's free. If not, I suggest you, if you are a member, I suggest you get it. There's also an IEEE document that was released a few years ago that discussed end winding vibration, and I know there's an IEC standard that has also published some literature on this phenomena. I actually participated in all of these, and unfortunately there's no international standard that actually goes as far as to give numbers. That's very unfortunate, because in reality, utilities, the only thing they do need is numbers. They can buy this equipment. They can have experts on site. You can take all the readings you want, but if you don't have an idea of how severe a result is, how exactly are you supposed to proceed? So we have our own standards that we publish that many utilities use, and we stand by those. In fact, I think those are the ones that should be in an international standard, but so far we haven't been able to convince, and not only us, some of our competitors also, we haven't been able to convince any international body to publish international standards.
Since this is a very interesting question, I would like to have a couple of minutes to explain the question and the answers from André in Spanish for our audience in Latin America. La pregunta es, ¿cuáles son los criterios para instalar acelerómetros para monitorear la vibración de cabezales de bobina en turbogeneradores? ¿Estas normas existen normas internacionales a este respecto? En realidad no existen normas internacionales. Voy a tocar un poco el tema al final de los criterios. Básicamente existen 4 criterios. Después de que una falla que causó una parada forzada a la unidad. Al encontrar evidencia de vibración cuando se destapa una unidad cuando ha parado, y cuando se conocen problemas, también cuando se conocen problemas de generadores similares en otras instalaciones. Y finalmente, un cuarto punto sería un tema de proactividad de la instalación, de las facilidades, para tener un sistema que les permita monitorear y aplicar el concepto de mantenimiento basado en condición. Luego que una falla, toquemos el primer punto, el punto de cuando ha ocurrido una falla. Y me ha tocado a mí, he tenido la suerte de estar presente cuando una máquina había fallado y la destaparon. Cuando uno encuentra fallas en una máquina, uno las repara. Pero ¿cómo está uno seguro de que esto no va a volver a ocurrir? La respuesta es colocar sensores que nos permitan, en aquellos lugares que han sido problemáticos, que nos permitan después tener una clara idea de cuál es el comportamiento de la unidad en estas áreas. Otro de los casos es cuando uno abre una máquina, digo abrir, uno las destapa para ver qué cosa hay dentro de una parada programada y encuentra polvillo blanco de manera localizada o de manera generalizada. Cuando es de manera localizada es más fácil porque uno tiene una idea más o menos dónde están pudiendo ocurrir puntos de alta vibración. Sin embargo, como son unidades que tienen refrigeramiento sea por aire o por hidrógeno y que el medio refrigerante circula a gran velocidad, este polvillo puede ser extendido a todo el interior y es un poco más difícil saber dónde han estado los problemas. También cuando existen señales de la evidencia de una especie de grasa o resina oleosa encima de las barras o en los cabezales. Esto es otra indicación de que altos niveles de vibración pueden estar ocurriendo en estos lugares. El tercer punto es cuando se conocen problemas en generadores similares al que tenemos en la instalación. Es decir, si nosotros conocemos que un generador de la misma familia de generadores en otra instalación ha tenido algunas fallas, es bueno, es saludable hacer una intervención dentro de una de las paradas programadas para instalar sensores que nos permitan monitorear en línea qué es lo que está sucediendo con esta máquina para saber si esta máquina también tiene los mismos problemas que hemos visto en otras instalaciones. Y el cuarto punto, que era el tema de la proactividad, podemos nosotros instalar un sistema previendo que no hayan problemas. Es decir, cuando uno tiene una parada forzada o una parada programada y encuentra problemas en la unidad, esta unidad va a estar abierta o parada por muy poco tiempo. El tiempo es oro en estos casos y en ese momento no existe posibilidad de instalar algo. Es decir, uno debiera programar la instalación de un sistema para que en una parada programada los sensores sean instalados y podamos ver de manera proactiva cómo se está comportando la máquina a lo largo del tiempo. Como decía André, desafortunadamente no existen no existen normas internacionales a este respecto, pero existen algunas guías o mejores prácticas de la industria. Algunas de ellas han sido publicadas por EPRI, que tiene un manual de mantenimiento de turbogeneradores, IEEE, que también ha publicado algunos documentos, y IEC, que también tiene algunas publicaciones al respecto de las recomendaciones que se deben seguir para el monitoreo de estas máquinas.
Oh, sounded good to me. Next question.
There's a couple of questions that we are receiving right now.
Okay.
The first one: what are the vibration limits when a machine goes overspeed or runaway? Any international standard covering these details?
Well, if we're talking about turbogenerators, obviously the end-winding vibrations are not really related to overspeed or load rejection tests. I'm sure in regards to shaft vibration, there are standards that are surely listed in the ISO standards. Depending on what type of unit you have, it can be a 10816-2 to -6, I believe. -5 is for hydro, but Excuse me, ISO 7919-5 for rotating parts. 10816 is for non-rotating parts. So it's 7919-1 to -6, I believe, probably cover vibration limits in those operating conditions, but obviously the vibrations can be or should be excessive in those cases. I'm not sure that ISO will cover results in regards to shaft vibration in those conditions. It's probably better to contact your manufacturer in those cases to get proper levels or compare to previous events that you've had on your unit.
Okay, we have another question now. What does FOA sensors used by VibroSystem measures double frequency vibrations and single frequency vibrations? Example, 120 Hz and 60 Hz, where 60 Hz are frequency vibration added by rotor into the end winding.
Well, our FOA sensors measure anything between 10 and 1,000 Hertz. So, they are finely tuned. I guess their best performance is around 100 or 120 Hertz, but they are still very precise at, I believe, 3 dB from 10 to 1,000 Hertz. So that's more than sufficient to look at end winding vibration or phase drops or phase leads or any of those components in the range that you want. The 50 and 60 Hertz will appear very precisely as well. There's some debate as to whether those are a source of concern or not. I believe they are. But in those cases, it's very important to make sure that you have some sensors on the core so that you're able to establish the 50 or 60 Hertz vibration that you're seeing on the windings or the phase drops or the phase leads is in addition to what is going on at the core, or is simply a transfer of what the core is seeing into the end winding vibration. Remember, if the core and the frame are vibrating at, let's say, 100 microns peak to peak, which is very high for a core, and you see the same 100 microns peak to peak at 50 or 60 Hertz on the windings, it means that the windings and the core are moving together. And if that's the case, the windings are not going to be subjected to any significant vibration because everything is moving. However, it will be an issue with the phase drops. And that's a case study that I've used before. It's not one that I have today, but a power station elsewhere, by elsewhere I mean not North America, had two major failures at the phase drops, and eventually we found, when I went to site, we found that the entire unit was moving vertically as the unit was in operation. So the core, the frame, the windings, everything was moving together at 50 Hertz, and it was causing the phase drops to be crushed, and eventually they cracked and failed. So if you're monitoring end winding vibration, phase leads, phase drops, and you want to see what the 50 or 60 Hertz is doing, it's critical to have a reference point on the core telling you whether the end windings or each of these components is vibrating at 50 and 60 Hertz as opposed to the core or in unison with the core. It's a completely different problem.
Okay, we have another question. It's a follow-up question, actually. How we can overcome end winding vibration, specifically during design stage and installation stage of the machine?
Well, the best way to do so, and in fact it might be the only way to verify the design, maybe not the design per se, but during the installation process, the best thing to do is bump tests. Bump tests are not frequently done on hydro generators, but it's a very, very important tool on turbo generators because the vibration at 120 Hertz, because of the extended end windings, they extend pretty far outside of the core, which is different than the hydro units. And because the length can be up to 2 meters, can be almost above 6 feet. And the end windings, other than having a consolidated basket, there's no support for that. They're actually hanging out there. So if you have excessive vibration there, it's a serious problem. So the bump tests will at least allow you to verify if you have natural frequencies that are near the electromagnetic frequency, 100 or 120 Hertz. And if that's the case, and I'll show you in the case study, if that's the case, you have to move that natural frequency away. Otherwise, the unit will destroy itself very quickly. You can't have a winding or a stator bar or any component have a natural frequency anywhere near the electromagnetic frequency, because they won't be able to dissipate that energy, and it is going to vibrate like crazy, and it's going to damage. Epoxy mica insulation hates vibration. It has fantastic electric properties. It has horrible mechanical properties. It's basically glass, and you can't shake glass for any significant amount of time or at any significant amplitude without having that material start to break. So it's very important to use bump tests to verify during installation. Now, you can have issues when the unit heats up that the natural frequency would change. So bump tests are very important during the installation stage, but you need to be able to monitor the performance of the unit while it's in operation to see if anything changes. And in fact, it will change. The idea is to monitor and see if those changes are creating a problem. Okay, so if you have end windings that expand, and they will expand, if they expand and that natural frequency goes down, anywhere near, once again, the electromagnetic frequency, you will have issues. And you want to find that out at the outset so that the manufacturer can go in there and fix it, other than writing or operating the unit for a certain amount of time and having a major failure. So it is important to do bump tests, and it's also important to have monitoring systems installed to be able to monitor and make sure everything is as expected.
And we have another question. Does VibroSystem have a universal end winding vibration tolerance guide for all kind of machines? Units have different size, different kind of isolation type, and every isolation having its own characteristics.
We have tolerances that apply to all different units, basically on the premise that epoxy mica, yes, you have different classes, you have different recipes, they have different performances, but as a baseline, you need something to tell you how severe it is. If you have a very high vibration value, maybe your insulation will last a little longer, but it's still being subjected to severe amounts of vibration. So we do have tolerances that we publish. I believe at the end of the case study, we're going to show you they are presented. And those, again, are used in many power plants. Well, we know that the vibration levels will affect insulation depending on the recipe, depending on the size differently, but those values still apply to all epoxy mica insulation. The levels should be below a certain level for you to be able to operate your unit safely.
And we have another question. This one comes from India. How an end winding vibration monitoring system can be useful for units that are, let's say, 4 or 5 years old?
Well, I think I touched upon that a little just in the previous question. Obviously, it's preferable to install an end winding vibration system at the outset so that you can, as I mentioned, be able to record the performance during the initial commissioning. When the initial heating up of the windings, you want to see how they react. As I'll show you in the case study, sometimes the windings don't react the same on the same unit. So it's important to see that initially, but even if you have a unit that's 4 or 5 years old, it's always a good idea to install monitoring systems so that you're able to assess the health, especially if you've opened it up and found evidence of vibration. The data can never hurt. At worst case, you can take a whole bunch of readings and you can learn about your unit's performance. For example, some units at different excitation levels, if you're producing VARs or consuming VARs, vibration will be completely different. And if you don't have a monitoring system, you'll never know about that until possibly you have a failure. So if you realize that when you're producing 100 megavars, that your windings vibrate tremendously at that reactive power level, it might be a decision for the utility to avoid operating in that range. And we've done quite a few case studies with turbogenerators and hydrogenerators where these types of operating conditions were detected and they were unknown before, and allow the utility to make decisions as to how they want to operate the unit. And again, if you can avoid these situations, you can extend the working life of not only the windings but the overall unit themselves.
And since this is a very interesting question, I take the liberty to translate it to Spanish for our audience in Latin America.
Okay.
¿Cómo un sistema de monitoreo de vibración de cabezales de bobina puede ser útil para unidades turbo que tienen entre 4 o 5 años de edad, quizás hasta más? Aunque es preferible instalar un sistema siempre de monitoreo de vibración de cabezales de bobina desde un inicio, el hecho de tener acceso a los datos es siempre valioso. Es como salir en un bote y no tener brújula. La brújula uno la necesita todo el tiempo. De la misma manera, con el monitoreo en línea de estos valores se pueden identificar áreas que al principio pueden no ser problemáticas, pero con el tiempo se convierten en problemáticas, en la que la vibración de los cabezales de bobina, colectores de fase y conductores principales de fase empieza a tener niveles excesivos, y se puede prever estas situaciones para tomar acciones de manera preventiva y planificar intervenciones en la unidad que estén orientadas a erradicar los problemas antes de que estos tengan un impacto mayor en la unidad. También se puede establecer línea base con la cual uno puede evaluar cómo la unidad va comportándose en el tiempo, y uno puede empezar a detectar que quizás mecanismos de falla iniciales que son casi imperceptibles empiezan a crecer, y uno puede evitar que ellos lleguen a niveles que no son deseados.
Sounds good.
The next question is from Mark Bissonette. Yes. Mark asks, although it's expected that radial vibration of the basket can occur, did VibroSystem observe vibrations in other axes? And if so, please explain observed causes or effects.
That's a good question. Yes, the instinct of most people is to install end winding vibration probes, in our case fiber optic accelerometers, in the radial direction, especially if you have no indications as to any existing issues on the unit. But we've had many cases where, for whatever reason, sometimes after measures were undertaken to fix a problem, a new problem occurred, as was the case in the case study I want to show you. It is important also to monitor the tangential direction. You know, the unit, if you look at it from one end to the other end, will obviously vibrate like this at 100 or 120 hertz. But it also is solicited tangentially like this, and it can be excessive. So it's important to be able to put we suggest one sensor. We assume that if it's vibrating this way in this location, well, it's vibrating the same at the bottom because it's one consolidated basket. And you put one sensor to be able to establish, is there this torquing motion going on? It is occurring, but how is it severe? Is it high? And in some other cases, you need to monitor the axial vibration, especially for phase leads and phase drops. Phase leads, as I mentioned before, are with the phase drops, they are the least supported components of the electrical circuit. And for phase leads, it's even more complex in the sense that they have multiple right degree angles. 90-degree angles to exit the unit, to cross over the windings, to go back down to the connecting ring, and then go down all the way to the phase drops, and then to the bushings and outside the unit. So not only is it least supported, but there's various angles, various magnetic forces involved, pulling and pushing on it. By far, they are the most susceptible to have excessive vibration, either caused by these magnetic flux patterns, and also because it has the most material, so it has the highest potential of having resonance issues. So in the case of phase leads and phase drops, just looking at the radial aspect, it can be insufficient. To be able to monitor the axial as well as the tangential is important. For phase drops, they also usually drop down below the unit. I have seen some of them exit up unit, but most of them exit down, and some of them can have issues, so you may have to monitor in three-dimensional directions to see how much of these bars and in what direction are they vibrating.
Since this is a very interesting question, I'm also take a couple of minutes to translate it into Spanish.
Okay, good.
Aunque es esperado que se produzcan vibraciones radiales de la cesta, VibroSystem ha observado también vibraciones en otros ejes. ¿Cuáles son las causas y o efectos de esto? Es importante monitorear las vibraciones tangenciales y axiales, especialmente cuando se monitorean los colectores de fase y conductores principales de fase. Es común encontrar fallas en estos componentes que son los menos soportados de todo el circuito eléctrico, y la prevención de estos problemas es muy importante. André ha trabajado en casos en los que los colectores de fase, y no los cabezales de bobina, eran la fuente de preocupación, tal como mencionamos en nuestro caso de estudio del día de hoy, en el cual la vibración ocurre en todas las direcciones. André también ha trabajado en casos en los que el movimiento vertical causaba fallas en los conductores principales de fase que van de la unidad hacia la parte baja. Por lo tanto, un sensor tangencial en la cesta puede ayudar a detectar movimientos que no solamente son radiales, sino que son tangenciales de la cesta. Y un sensor, un acelerómetro en la dirección axial para detectar posibles vibraciones transmitidas por el eje a toda la unidad o de naturaleza electromagnética. Este criterio aplica en general para todos aquellos elementos que no están soportados dentro de una cesta consolidada de cabezales de bobina. Okay, let's jump to another question now. Let me see. Okay, we have another question here. How much percentage of unit damages in the world due to end windings is due to end winding failures? Is there any statistics about the cause of unit damages?
Statistics, I'm sure there are, especially if you ask insurance companies. I personally don't have statistics on end winding failures per se. I know for a fact that the biggest or the most common failure on generators, be it turbo or hydro, is guide bearings. Guide bearings by far fail the most often. They don't fail necessarily often, but they fail the most often. But I also know for a fact that if you ask insurance companies what is the most costly failure on a generator, and that is by far end winding or stator bar failures. And the reason for that is the turnaround to have new windings, if the failure is excessive, and unfortunately in many cases it is, the turnaround is quite long. And the fact that if you do have an end winding failure, face to ground or face to face fault, chances are the core is also damaged. Now that's an even bigger issue. In most cases it can be repaired, in some cases it can't. So when you look at the damage involved and the turnaround time to get new parts, get resources mobilized to do the work, the amount of work to be done, in many cases the outages are much longer than guide bearing failures. So from the perspective of insurance companies, winding failures are by far the most costly general failure on generators.
We have another question now. What should we look for during an outage of a turbogenerator?
In regards to end winding vibration, as I mentioned before, first thing to look for is dusting. If you see dusting, and dusting caused by fretting, not localized dusting caused by partial discharge, and they're very easy to differentiate. If you have dusting between a conductive component and a non-conductive component, obviously that's vibration. It's not partial discharge. If you see dusting between the winding and the core, well, that's probably sparking, and that's caused by electrical concerns. As I mentioned also previously, if the unit is moist, has humidity, like in air-cooled units, you will find greasing because the moisture will mix with the dust, and it will create this brown gunk, the brown grease that you will see either leaking somewhere locally, or you will see it spread all around if it's really, really bad. Another thing to look for is damage to ties. If you see ties that are cracked, broken, entirely missing, that's a clear evidence of vibration as well. If you see support blocks that are loose or missing, or you can find them on the floor, that is also a clear sign that you have vibration issues. And in reality, those are even worse, because if you start losing the components that are part of the actual structure holding the thing in place, those natural frequencies we mentioned previously are going to change. And when they bump test the unit, everything is tied up, everything is supported, everything is in its final state. And if you start losing tightness because the ties are breaking off, or if you lose some of the support blocks, all of this will completely change the performance of the windings. And if that's the case, usually you'll see the natural frequency go down even further, closer to the electromagnetic frequency. So evidence is dusting, greasing, cracks, broken ties, missing ties, loose support blocks, missing support blocks. Those are all evidence of end winding vibration. Now, the question, if I remember correctly, was about during an outage of a unit.
Yep.
It's not just end winding. Well, obviously, if you have the chance to inspect the core and the frame, you may find some problems with grounding issues. We have a few cases presently where the core and the frame don't work together, and it creates some sparking between the core and the frame, or the key bars in the core, or the key bars in the frame. And that's high energy sparking that can seriously cause damage, can actually melt the core if you leave it unchecked. So those are things that you should also take a look at. And if you do find issues, you should install piezoelectric accelerometers on the core and on the frame to see if the unit during operation is working together, if the core and the frame are working in unison, or there's some lag or some offset between them, showing that there's some kind of looseness between them. So that's another aspect that you should look at in regards to the stator.
And we have another question here. Why monitor the end winding vibration at the drive end?
Well, most people, and I've had this discussion on many occasions with utilities and also with manufacturers, and the premise, which makes sense when you listen to the actual comment, it makes sense. But the idea is that, well, you know, the drive end, there's not a whole lot of material there. I mean, there's no phase leads, there's no phase drops. It's basically just the winding coming out and going back in the unit, which is true. And it is also true, as I mentioned before, that on the non-drive end, because you do have those phase leads coming out of the unit, and then they go to the connecting ring. There's a big series of connecting rings in the back, and that goes to the phase drops. And there's a whole bunch of material there, again, that is least supported material that can easily have resonance issues or can vibrate because they're not as supported. However, statistically, the projects that we've been involved with, and I gave some of that information to help produce the EPRI guide, we find as many failures on the non-drive end than on the drive end. There's no, the epoxy mica doesn't like to vibrate. It doesn't matter where it is, doesn't matter if it's on the non-drive end or on the drive end, it does not like to vibrate. And if you have resonance issues, looseness issues, problems with the support system, you will have high vibration on the drive-in as well, and you may have, failures on the drive-in as well. So, I mean, if the drive-in fails, the unit is still out for a certain amount of time before you fix the issue. So, we strongly recommend monitoring both ends to make sure there are no issues on the drive-in or on the non-drive-in.
We have another question also. What is the acceptance criteria for bump test results?
Well, there's some discussion about that from different, I guess, consultants, because there are companies that do that for a living. They perform bump tests. And in fact, the case study I'm going to show you, one engineering firm, very large engineering firm in the state, was involved. Usually, what we recommend is that you should not be in an exclusion zone, which is defined by 5 hertz less than the electromagnetic frequency, or 10 hertz above the electromagnetic frequency. So for example, if your magnetic frequency is 120 hertz, you should not have any results from the bump test that are between 115 or 130 hertz. Anything inside there will be a problem, okay? Now you notice there's a higher range above, and that's because, as I mentioned before, when you heat up the winding extends, it expands in all directions, and that changes its frequency response. And we know, based on experience, that frequency, that natural frequency will go down. So down is going to go closer and closer and closer to the magnetic frequency, which is going to create tremendous amount of vibration. In the lower end, usually if you're 5 hertz away, again, the natural frequency will also go down as you increase the heat, so it's going to move away from the magnetic frequency. So the criteria is for 120 hertz units, it's no results between 115 and 130 hertz. If it's 100 hertz units, nothing between 95 and 110 hertz.
We don't have more questions for the moment. Maybe we should go now to our first case study. If you let me just a second,
okay.
Andrea,
Sorry.
I'm gonna leave you the control in a second.
So this
there you go.
This case study was This case study was in the States, in the New York City area. It was a combined cycle plant, and the company was building the main generator, the steam turbine. And while they were doing that, they learned that an identical generator somewhere else had experienced severe problems, in fact, a failure, within a year of its initial commissioning. Now, they did not want to have that same problem. So what they did is they took a whole set of measures to try to make sure that they didn't have the same issues. And we're going to take a look at this. First of all, signs of excessive end winding vibration, what to avoid? Well, it's important to understand the unit behavior, and understanding the unit behavior is critical. Many utilities have witnessed clear symptoms of excessive vibration during outages. As I mentioned before, you go in there and you see signs of fretting, which is powder and or greasing. Sometimes you'll see both. And as I mentioned, signs of broken ties, loose blocking, when vibration levels are severe, cracks in the insulation are also all signs that there are some severe issues. Here are some examples. You can see on the left, the red is dye that the customer put on there to try to find some evidence. But the problem here is this brown stuff. Okay, so this is basically dust, which is created by the rubbing between the insulation and the support, either the ties or the support blocking. And that dust mixes with moisture and it becomes this brown stuff that we see all over the place. So this is definitely an issue. Second, which is even worse, you can see that the tie here is completely broken off. The tie is going across here and holding these two windings. Well, there's nothing holding these two windings anymore because the actual tie has broken off completely. It's severed. And this one is in the process of doing so. It's already halfway broken off. So there's obviously a vibration issue on this unit because of the broken ties and also because of all the grease that is present on the windings. The second one is, well, I wanted to show you what a severe failure looks like. This is also a power station in the United States, and we can all see that there's actually missing material here. We have the what's left off of the copper, and the winding, which is supposed to go here to the end cap. Well, that's all gone. It's people say, well, it melted off. No, it did not melt off.
Evaporated.
It evaporated off.
Yeah.
Okay. It took a millisecond and it evaporated. And for those who wonder, did they have to replace the entire winding? No. There's a company that actually went in there and fixed this. Okay. So they were able to make a part that was put on and actually brazed onto that, and it's a company. If people are interested, I can give you the name. I don't want to use the name in case for whatever reason they wouldn't want us to use it, but they did a fantastic job of actually fixing that and putting the unit back online. Okay, so that's quite amazing. Now, again, after hearing that a unit somewhere else had a major failure, a well-known American engineering firm was hired to perform bump tests. Okay, so they were in the process of, they were almost finished assembling this unit, and the utility said, well, we want to make sure we're not going to have the same issue, so let's bring in this company to do bump tests. Now, before the bump tests were performed, the manufacturer decided to replace the dry ties that had been installed with wet ties. Okay. Now, dry ties are common, but in the last 10 years, when vibration issues occur, one of the first things the manufacturers recommend is to replace the dry ties with wet ties. Wet ties create a much better chemical bond with the winding insulation, and it greatly reduces the vibration levels by providing better support. The dry ties were pretty good, but in some cases they were not actually holding the bars in place because of the way they're installed, and eventually the bars would become loose and would rub against the dry ties. So wet ties are a much better solution. Here's an example of the actual bump tests that were performed on a few bars, and you can see their exclusion zone was, as I mentioned, 115. In their case, it went up to 135. That was their exclusion zone. And anything in this zone is considered a problem. Now, you can see there's some activity here, but you might be able to get away with it because it's not that close to 120. If they operate the unit, that natural frequency will go down, but it might still stay away from 120. But you can see that this one, the amplitude is higher and it's closer to 120, and this is completely unacceptable. Okay? This is way too high and it's pretty close to the 120 hertz exclusion zone. So, in April of 2011, they purchased 17 fiber optic accelerometers from us, and they were installed to monitor the unit's performance. Now, as you can see, 12 of these were actually installed on the phase leads. You can see one here, you can see a second one there. Okay? We can see a few sensors in those locations, because the bump test results were, the worst results were at the phase leads. So they installed most of them, 12, on the phase leads. But they installed 3 on the phase drops to make sure there wasn't an issue there. They installed 1 on an end cap, but to look at that tangential movement, potential movement. And they installed 1 on the back of the core in the radial direction to see how much of the movement recorded on the phase leads or on the end cap was transmitted by the core or is basically as opposed to the core. It's always a good idea to have a reference point. The installation process was supervised by VibroSystM certified technicians. This sounds self-serving, but we always not only recommend, we always hope that the utilities will hire our service department to do the installation, because there's a few ways to do it correctly. There's a million ways to do it incorrectly. And remember, folks, we're installing equipment on very high voltage. It's a serious business. We do not want the equipment to cause any issues to the unit. We do not want the harsh environment to damage our sensors. And first and foremost, law number 1 in monitoring is we do not want to harm or kill anyone. So this equipment has to be installed by people who know what they're doing, by people who know what not to do to put lives of people in danger.
Excuse me, Andre.
Yes.
The installation of these accelerometers can be done at the manufacturer's facility, right?
Yes, yes, yes. In some cases, the manufacturers are hesitant to allow people or utilities to buy monitoring systems and have them installed for various reasons. And in many cases, the utility asks the manufacturer if they will allow us to go at their plant and install it. And so far, all cases, they agreed with that approach. So that was not an issue. So long as it was done at their plant, with their supervision, with their input, they are quite comfortable with that. So if you're thinking of buying a monitoring system for a new unit and you're getting this pushback from manufacturers, suggest that we go to their plant and install it, and I'm pretty sure they will agree to that. So it's a good point there, Paul. So as you can see, the fiber optic cables follow with the end windings. I won't go into all the details. If you wanted details in regards to installation, I strongly suggest that you send an email to our service department at service@vibrosystem.com, and they will answer all the questions you want in regards to the proper installation of this equipment. And to hold everything in place, we use epoxy impregnated tape so that the cables are held permanently on the windings, and because of the epoxy impregnated feature, they will stick to the insulation and they do not come off. So the fiber optic cables are routed all along the connecting ring, and they exit through sealed tied flanges. The flanges are designed to prevent hydrogen leaks. That's another thing we don't want to create. We don't want to show up at site and start creating hydrogen leaks. The signals that were, in this case, the signals were tested and then connected to the power plant's protection system. In their case, the acceleration was integrated into displacement, so it was integrated into mils peak to peak. We rather see velocity, but many utilities relate better to displacement than velocity. So they set it up this way so that they could alarm on it. And then the unit was put back online. Now we can see here 8 sensors. We can see the results, and the results here are only at 120 mils. We had results, of course, at different frequencies, but the results we're focusing on here is 120 hertz. And you see here our own tolerances. We believe anything less than 2 mils peak to peak or 50 microns peak to peak is excellent. And many units, as you can see, are able to reach that level. Anything between 2 and 12 mils peak to peak or 50 to 300 microns peak to peak, that is also acceptable. Anything 12 to 20, which is 300 to 500 microns peak to peak, is considered high, and anything above 500 microns peak to peak is considered critical. Okay. Now, all the results I've given you here those tolerances are true so long as there's no evolution. Okay, that's very important. As with most parameters on a unit, if you have a high level but it's stable, that's a much better result than having a low value that's increasing. Because if it's increasing, it means something's going on. Something is evolving. If you're not changing the operating condition of the unit and you have a change in performance of any parameter, that's a problem. Something is evolving that you need to take care of. So if you get a 10 mils peak to peak reading, that's not the result you would hope for. But if it's going to 12 and then to 14 and then to 16, you have a problem. You don't need to wait till you get to 20 mils peak to peak. You need to intervene before you get to that point. So you can see the results. The worst case was at this sensor here where we had 20.9 mils peak to peak, which is above 500 microns. It's above the 20 mil tolerances. So this was unacceptable. For a new unit to have that type of result, that's totally unacceptable. So these levels were taken in August of 2011. We can see additional sensors. As I mentioned, 17 of them had been installed. And we can see that we had another sensor that was seeing some slightly high levels, 12.8 mils, for that particular end winding. So those results were worrisome. We have an example here of the raw signal and the FFT showing the 120 hertz. Okay, so the software is able to take readings and give you the results in frequency. So our recommendation was that efforts should be made to investigate the high vibration levels. End winding vibration monitoring should be performed on a regular basis. And unfortunately, in many cases, people just hook up the system to PLCs and put alarms and they only intervene if there's an alarm. They don't actually take readings on a regular basis to see how the unit evolves. Okay. So in October 2011, the collector end was opened for inspection prior to the expiration of the warranty, and then a robotic air gap inspection was done and limited electrical tests were performed. Red eye and resin repairs were carried out to address significant dusting issues. Now, in March 2012, and this is what I found very interesting, is that not only were the vibration levels high, but in reality, we saw some conflicting results. If you look at this section here, you can see that as they varied the operating condition of the unit, the vibration for those sensors went down. But at the same time, some sensors were seeing an increase. Now that's worrisome. It means that the end winding basket excuse me, is not functioning symmetrically. When you change the operating condition of the unit, some vibration goes down, some vibrations go up, some vibrations go up together. So there's no symmetry, there's no reaction of all sections at the same time. So that's, for us, was a clear indication that the end winding basket was troublesome. It was problematic. You can see here vibration increasing while it was decreasing at other locations. So that was a clear indication that the support structure, it was having some issues. Okay, so here's a picture when they opened the unit, and we could see a whole bunch of dusting. It's not that easy to see here, but we could see that there was a significant amount of dusting on this new unit. In March of 2013, the collector end was opened for proposed blocking modifications, consisting of replacing all the blocking between the phase connections using conformable packing. End winding area was repainted, bump tested, and we did a battery of electrical tests. Again, in March 2014, the collector end was opened up. 2013 blocking modifications were unsuccessful. The conformable packing was removed, new blocking configuration. So the manufacturer did a whole bunch of work to try to reduce the amount of vibration. So they did bump tests again, they repainted. Effectiveness of the 2014 end winding blocking repairs were verified in October of 2015. Although a significant improvement was observed, the following photos identify the areas that still continue to exhibit a moderate level of dusting from fretting. Okay, so you can see evidence of dusting that was found left and right. Okay, so this was evidence that it was still vibrating, although a lot of actions were taken to try to fix this. It was still going on. So the manufacturer reviewed and discussed the results with the personnel. It was agreed that the dusting was moderate and that there was no time to make repairs. So the conclusion was to apply wicking resin after the cleaning, and a longer-term repair solution would be to replace the entire collector blocking with the new manufacturer configuration. The customer continues to closely monitor the end winding vibration. We are in close communication with them on a regular basis, and they ask us to review data on a regular basis. The results show that although the radial vibration levels were reduced, so the actions of the manufacturer helped reduce the radial vibration, but then we saw axial vibration levels that were now high. So the problem was being transferred somewhere else. They were putting Band-Aid on one part, and it was causing the problem to migrate to another part. Tangential vibration levels also increased. So we can see now radial values were still high for this sensor. This sensor had good results, but the axial results were now very high. You can see there's 3 locations on this graph that show that the vibration levels were very high. And in this one, it shows that one sensor saw an increase in tangential vibration. So the problem was still there, but it was moved around. So it's critical to have a complete condition monitoring system installed during commissioning. They were able to do this initially, and thanks to the data collected by the Zoom monitoring system, coupled with the experienced data interpretation specialist, discussions with the manufacturer were possible so that a solution could be implemented at the earliest convenience. For the moment, elevated vibration levels still exist. Continued monitoring is performed with the help of VibroSystem. It's important to mention that the manufacturer, and this is true, it is still true, collaborated throughout various stages of this project and made all necessary efforts to assist the customer. Astoria remains confident that with the help of the manufacturer and the data provided by the Zoom system, the unit will continue to provide power in a reliable fashion for its entire expected working lifespan. And in fact, the manufacturer, I think, has still extended the warranty on this unit. So despite all the problems they had, they were still able to make sure that this unit ran continuously.
Okay. We have no more questions for the time being, André, so maybe we can wrap it up.
All right. Well, thank you all for being here. I hope it was interesting. I think it's not just cold outside. I think it's a little cold in here. My hands are frozen. Don't forget to subscribe to our YouTube channel, and don't forget to ring the little bell so that you can get notifications if any new content becomes available. Don't forget to write your comments or questions at the bottom of the page. After the session, we will answer them during the Q&A session, which will be held in October 8th or on October 8th, which is in 3 weeks.
The videos will remain permanently on our channel, so you can listen to them in any time in the future.
Correct. So as you can see, we're trying new formats. We put a little more emphasis on a paper today. We didn't have time to do the hydro one, but we can do that in a future session. So we're trying to address different needs, different requirements, but we would like to have your feedback, your comments. If there's subjects you would like us to cover that we haven't so far, let us know. We'll make sure we do so. If there are case studies that we've done in the past that you would like us to revisit, to develop them, to add a little more information, allowing you to ask more questions about them. If you have certain subjects that you want us to cover, if there are terms that you hear left and right, you're not exactly sure what they mean, you would like us to cover that so that you can have conversations with your colleagues, we can do that as well. So any suggestions, any comments you have will be looked at and considered seriously. And again, as I mentioned, if you have any questions for us in my department, you can send them directly to diagnostics@vibrosystem.com. If you have questions of a technical nature, as I mentioned before, you can send an email to the service department at service@vibrosystem.com. If you have any questions about pricing, delivery, if you want to have information on business managers in your area of the world, you can send an email to sales@vibrosystem.com.
You can also contact us via the comments below, or via our LinkedIn page or website, or via Facebook.
Yeah, so go and see our Facebook page, our website. There's a lot of information there, and I'm sure it might trigger some questions or comments for future Q&A sessions. So on behalf of Paul and myself, it was a pleasure to be with you for this short hour. Be safe, and I hope to see you during our next Q&A session. Thank you.
Thank you very much. Hasta la próxima.
Thank you.